All right, section 2.4 is really the last of the rules that we're going to look at in chapter 2 about finding derivatives. It's kind of the last piece we need to be able to take derivatives of just about everything we're going to encounter this whole semester. Okay, so this is called the chain rule. The chain rule has to do with what happens when you have functions embedded inside of other functions. So imagine having something like x squared plus 2 and it's under a radical, right? Or x squared plus 2 and it's in a denominator that's going to be cubed, right? So you have something that's inside of another function of x. Those kinds of functions are called composite functions. You encounter them in algebra courses, either in an algebra 2 class, maybe in high school, maybe a pre-calc class, maybe you took a college algebra class. That's where you see composite functions for the first time. And that's how you see this showing up. The g of x is inside of the other function f of x, and we're taking the derivative of all of it. So jot down how that works, and we'll talk about it. Okay, so if you can imagine that g of x, which I'm going to highlight in blue, is my inside piece, what this says is that first I look at the outside function, whatever's happening on the outermost piece of this equation that we're working with. And I take its derivative, and I simply rewrite the g of x where it was before. I don't do anything with it. And then after that, I take the derivative of that inside blue piece, and I multiply it by what I had already. Okay? If the functions are not too difficult, right, they're pretty straightforward, simple functions, it's not a very difficult process. The problem is when this mixes in with products and quotients, and things can get pretty messy pretty quick. So we'll start off easy, something that's pretty clean and straightforward. So if you take a look at this one, you could use algebra and avoid the chain rule. What would you have to do? You'd have to actually multiply what's inside the parentheses by itself 5 times. Probably not your best friend in terms of like doing something efficiently. I don't want to multiply 6 minus x squared out 5 times, do you? No. So the chain rule actually works out to here very nicely so that we don't have to do that much work. So here's what I'm going to do. I'm going to highlight, just like I did on the previous slide, the inside piece. This piece is inside the power of 5. So I want you to just focus on what's going on the outside. That is the part that's not highlighted in blue. So on the outside, I have a 2 in the front, and I have a power of 5. So it's almost like this. I have this function that's just 2 blue to the 5. It's 2 blue to the 5. That's all I have, 2 blue to the 5. Well, what do I do when I have a power of 5? Yeah, you do the power rule, right? The one you just did on the quiz. So what do you do with the power of 5? You bring it down to the front, right? So the 5 gets multiplied by the 2 to give you 10. And then you decrease the power by 1. So if I decrease the power by 1, it will now be a 4. Okay, I've purposely left the piece inside blank because that's not what I'm dealing with. I'm just looking at the 5, bringing it down, and decreasing my power. Is that part okay? Okay, so the chain rule says that whatever I highlighted in blue there, that piece that's inside, just drops down and it's inside again. So it's 6 minus x to the 5th as well. It doesn't change. It just gets rewritten. Kind of like the 2 itself comes along for the ride, that piece just comes along where it was before. And then after that, I multiply by the derivative of the inside. So now I do need to take the derivative of the 6 minus x squared, but I don't take the derivative of it and stick it inside. I multiply it on the outside afterwards. So what's the derivative of 6 minus x squared? Yes, it's negative 2x. Yes?
So why is it 6 minus x to the 5th power instead of x to the 2nd?
Does yours say second? No, it says 5th. Okay, so ask the question again.
So I thought you just plugged in the g of x, so why would it be the 6 minus x to the 5th instead of 6 minus x to the 2nd?
Oh, I had a typo here, is what you're telling me. That's what it is. It should be.
Oh, okay.
I just wrote it wrong.
Okay,
Yes, so sorry. I didn't mean to do that. Okay, is that better?
yes.
Everybody okay now? Okay, so on a gateway, we would stop here. But for what we're doing, there's no reason that we can't clean this up. The pieces that we can clean up, oh, I should change colors because I was using blue to represent something specific, is the 10 on the outside. Let's try red. The 10 on the outside and the negative 2x. Those can be multiplied together. Right? The piece that's still got a power of 4, I don't want to distribute that out, so that's not going to be able to combine with anything. But if I take the 10 times the negative 2x, what will I get? Yeah, so I have negative 20x, and then I have 6 minus x squared to the power 4. And that's the chain rule. Is that okay? Okay, one that just had a chain rule, that's how we're starting. This is another example of one. You could use the quotient rule on this. Let me just say that real quick. You could totally use the quotient rule on this. It's really not a natural way to do it because the derivative of the numerator is 0. So that kind of makes it feel funny to use the quotient rule, but it would work. You just have to make sure that when you take the derivative of the top, you get 0 when you're doing that. So quotient rule will be okay. But the chain rule works along this very nicely. So remember we had an example in a previous section where we had 1 over x and we rewrote it as x to the negative 1? Yes? We're going to do that. But we're going to take the entire denominator and write it to the negative 1. So I can take the entire denominator, x squared, plus 3x minus 1, and write it to the negative 1. And if it's written in that form, it actually looks a lot like the previous problem, doesn't it? It does. So we're going to do the chain rule, because that's what we're practicing anyway with this. But if you wanted to use the quotient rule, you know you could totally do that, right? Yeah. Okay. So I'm going to do that highlighting the bit again with the inside. The inside is often in parentheses, so that's one way to kind of identify it. It's not always, but it's often in parentheses. So I really just need to look at what's happening on the outside. That is the power negative 1, right? So the power negative 1, much like the power 5 on the previous problem, is a power rule. What will I do with the negative 1? I'll bring it down in front. And I will subtract from the exponent. So if I have negative 1 as my exponent and I subtract 1, what do I get? I get negative 2. And then what do I put inside the parentheses? The same stuff that was there before. X squared plus 3x minus 1. And then on the outside, I need the derivative of the blue stuff, right? The stuff that I just dropped back into place and didn't manipulate. So what is the derivative of x squared plus 3x minus 1? 2x plus 3. So we stop here on the gateway, and we're all happy, okay? What do we have to do when it's not the gateway? Well, we didn't have negative exponents to start, right? And now we do. So I want my negative exponents to be put back into a positive form. How can I change this so that that negative 2 as an exponent is no longer negative? Yeah, I can drop it back into the denominator, right? So I'll do that part first. The denominator can have the x squared plus 3x minus 1 squared. And that kind of shouldn't surprise you because I told you we could do the quotient rule, and if we did the quotient rule, the denominator would be squared. And that's the original denominator now squared. Right? They have to work out to being the same thing, or otherwise they wouldn't both be valid. And then on the numerator part, I simply need to multiply the negative 1 at the beginning and the 2x plus 3 at the end. So what do I get when I multiply the negative 1 at the beginning and the 2x plus 3 at the end? Negative 2x minus 3. And that is g prime of x. Okay, is that all right? All right, I'm going to show you the next problem and talk to you about why there's 2 different ways to do it, but then we're not going to do it because it'll take too long to actually delve into this problem. So on this one, tell me some things you see. Let's just start there. What do you see?
All of it's to the 1/2.
We could write all of it to the 1/2. That is one option. We could write everything to the 1/2. What do you see on the inside, though? There's a quotient. So I have a quotient rule, And the quotient is inside of a chain, isn't it? Yeah, that makes the problem kind of messy. Now, this isn't the only way that I could rewrite this, though. This is definitely one option, so that I leave it. I'm not going to rewrite the piece, but I leave it like it was, just to the power 1/2. The other way that I could rewrite it is I could rewrite each individual piece to the power 1/2, right? What's the difference? Well, in the first case, I actually have an inside function of a chain, right? And the inside's a quotient rule, like we just said. The second way that I rewrote it, what I actually have is I have a chain rule on top and a chain rule on bottom, and the quotient rule is the outside function. Will they both give me the same answer? They will, if they clean up to the same point. They'll give you the same answer, but they're two distinctly different ways of doing this problem. I mean, completely different. They look very different, and if we stop at the gateway point, the answers look completely different. What that means is my answer keys have like multiple options as what I'm looking for when I look for your answers. But we were going to do both ways next time, just so you can see how they work out. And then after that, you can decide which one you liked better and just forfeit the other piece and ignore it. But that's what we're going to pick up on next time. Okay, so our homework from 2.3 should be completed before next time, and we will finish 2.4 in class.